Okay, good. So let's talk about group. So a group is a set of elements that satisfies specific conditions. So if we take any random set like this, we may not be able to find some interesting property of this set because it's not really following any of the group conditions. On the other hand, if we take a set of integers like this, and then 0, 1, 2, 3, and so on. So a group is always defined with two things, one being the set of elements, which in this case is a set of integers, and the second one is group operation. That is for the time being addition or multiplication. Although you'll find in abstract algebra books that a general group operation is defined with a tiny circle like this, so A times B, where this operation can be anything, addition or multiplication. So going back to our example, the set that we have is the set of integers, and let's consider addition as our group operation. So you can check if we add any of the two integers, for example 2 plus 3, that gives us 5, which is again an integer and it belongs to this set. You take any two integers and add them together like this, and you will find an integer belonging to this set. It will never happen that you add any two integers and you get a number that does not belong to this set, because integers are closed under addition. We call this property the closure property. It means you take any two elements, perform group operation, and the result is still inside that set. The set is closed, and this may not be the case in our first set, where if we add 2 and 3 we get 5, and 5 is not present in this set. So we say that the set S is not closed under addition. Then the second condition or property is the associativity, meaning if we take any three numbers like this, three integers, then performing 3 plus 5 before this operation is same as performing 2 plus 3 before the second addition operation. So the order in which we perform the group operation does not matter. This we call as associativity. Then there's one special number in this set of integers, and that is 0. If we add any number to 0, any integer plus 0, we get back the same integer. 0 plus 1 gives back 1, or 0 plus 5 gives back 5 itself. So we say that there exists an element which acts as an identity. So this is the third property, existence of identity, and it means having a group operation of any element in the set like 1 or 5 with this identity gives back the same element. And finally the fourth condition, and that is existence of an inverse. So if we add together -3 and 3, we get back the identity, that is 0. So we say that for each element there exists an inverse of that element, which after group operation gives back the identity element. Notice how I've written subtraction here. So instead of writing 2 minus 2, which becomes an entirely different operation, instead of that we write 2 plus, where plus is our group operation, -2. This way we don't have to introduce extra group operation, that is subtraction, and instead we can simply have addition and the inverses to define subtraction. So let's write a generalized definition. So we can write a group G along with a group operation satisfies the following conditions. If some element A belongs to this group, and then there's another element B which also belongs to this group, then this implies that A group operation B. So instead of saying group operation, let's just say A times P. Don't get me wrong here that by A times P I mean to multiply them. This group operation can be anything, addition or multiplication. Let's just use the word times instead of group operation. So A times P will also belong to this group G. This is the closure property that we discussed here, the first one. If 2 is integer and 3 is integer, then their group operation is also an integer. So a group is closed under its group operation. Then we have associativity, which says A times B times C, with P times C happening first, is same as A times B and that times C. This property is associativity. Then there's existence of an identity element. So there exists an element E which belongs to this group such that A times E is same as A for all A belonging to group G. Okay, and finally we have an existence of inverse, which says for all A there exists an element denoted like this which belongs to the group G such that A times A inverse gives us an identity element. So this is the formal definition of a group. Now few points to add here is that there's no restriction on the number of elements present in the group. There can be infinite elements as there were in the integers, or there can also be finite elements group. We will see an example of that. Then the next point is that although this is valid here that A times P, or I should say A plus B in our case, is same as B plus A, this property is called as commutativity. So addition and multiplication of numbers is commutative, which means if A is on the left or B is on the left, that does not matter for numbers. But if we have a group that has matrices as its elements, then the order does matter, and in that case the group is not commutative. So there's no restriction that a group should be commutative or not, and if needed we can identify a group as a commutative group or non-commutative group, but our general definition does not care about that. Let me get rid of this. And finally, the order in which identity element and the inverse are applied, that does not matter. Meaning, if I apply identity from the right, some people like to call it right identity, it is same as left identity, and both gives us the element A, and similar is the case for inverse. Inverse applied from left or right gives us an identity element. This will always hold even if the group is commutative or not commutative. So A times B may or may not be same as B times A, but A times E, the identity elements, will always be same as E times A. So don't get confused here with group as a whole being commutative and these two multiplications being commutative. Okay. Now let's look at some examples. So we already saw one example, that was integers under addition. So we define this group as this. It of course satisfies closure, associativity. There exists an identity element, to be precise, additive identity. And also there exists an additive inverse. We just saw how integers satisfy these four group conditions under addition. But can we say that integers under multiplication forms a group? The answer is no. If we check conditions one by one, so closure, if we multiply any of the two integers like this, then of course we get back an integer. So closure is satisfied. Then you can check associativity. Is also satisfied. You can check by multiplying any three integers. Then again there exists a multiplicative identity. If we multiply any integer by 1, then we get back the same integer. So nice, identity is also satisfied. But wait, the final property, that was an existence of inverse, it is not satisfied, because if we take 2 and then to get an identity element, we have to multiply this element with its inverse, multiplicative inverse, which will be 1 over 2. But this is not an integer, it does not belong to this set Z. So the property existence of an inverse is not satisfied, and hence we say that integers do not form a group under multiplication. But there's a good example, and that is real numbers. Real numbers under multiplication will form a group, and as well as under addition they do form a group. So you can check these four properties for these two cases. You can drop a comment if you face any difficulty in this exercise. And finally, let me give you a simple but strong example of a finite group that has only 3 elements. People like to call it a cyclic group of order 3, and it is defined as, I should say it is given as a squared, a cubed, where a cubed is itself an identity. So you can see if you multiply any two elements like a times a squared, we get a cubed, and it belongs to this set. Okay, then if we multiply a squared with a cubed, as we have already defined it to be identity, we get back the a squared. So this also belongs to the set, and similar is the case for multiplication of a with a cubed. Now don't get confused, like how can we write a to the power 5 as a squared? This is because by definition we are saying that a cubed is an identity element. So with that said, it follows closure. Associativity is also followed, like you can take multiplication of a squared and a cubed. The order in which we do the multiplication does not matter. Okay, so associativity is also satisfied. Identity is predefined, so the third property is also satisfied. And for the inverse, a is the inverse of a squared and vice versa. So if we take a times a squared, it gives us a cubed, which itself is an identity, and that means they are the inverses of each other. And so inverses of all these elements exist. 4 group conditions are satisfied, and we say that this set G forms a group under multiplication. But you're still stuck on this A cubed, right? I know you are, so let me just clarify that. Let me choose a different color. So each of these elements can be thought of as rotation of an equilateral triangle. If we just colored its vertices like this, let's give yellow here and the blue one here and the green here. Now if we rotate this triangle in counterclockwise direction by 120 degrees, so we are rotating about its center, and that will give us the same triangle, but these colored vertices will change their position now. So the green one will go here, yellow will be here, and then the blue one will be here. If we repeat that thing with 120 degrees like this about its center, then again the position of those colors will change. So the green one will now go to this position like this, the blue should be here, and the yellow will be here. And you repeat that again with 120 degrees, we will reach the first position like this. So we will then have the green color here, yellow here, and the blue one here. So we got back to original triangle. But did you notice something? We applied the rotation 3 times here. So if we say that A is nothing but a rotation of 120 degrees for this triangle, then A cubed will be a rotation of 360 degrees. And we know that if we rotate any object, any shape in 2 dimensions in an angle of 360 degrees, we get back the same thing. So that is what is happening here. A cubed is an identity element as discussed here. It gives back the original object, while A squared is a rotation by 240 degrees. So I hope the picture is much clearer now. This A squared and A cubed are representation of rotation. And similarly, we can have cyclic groups of higher orders like order 4, 5, 6. We can also have a group of reflection and rotation. If we reflect this triangle about this axis or this axis or this we can call as reflection about axis passing through A vertex or B or C like this. Then along with this A squared, A cubed, you will have additional reflection elements in your group. So this is how it goes. You can take any object like continuous functions or matrices or polynomials. You can find group structure there. You just have to satisfy those 4 conditions: closure, associativity, existence of an identity element, and existence of an inverse. As long as those are satisfied, groups are there. And groups have many applications, be it chemistry or particle physics or spectroscopy. Group has applications in all these fields. Not fields, I should say area, because fields is another mathematical object that we're going to discuss in coming lectures. Until then, I'll see you in the next one.